Start? All right. Okay, so we are in the ninth innings, as you say in America, or the last lap or whatever. I might run over, so let me start by acknowledging the people who actually did the work. Bhandawat Vikas is our long-term collaborator on everything biomechanics, and Ali Tehrani Safa is a postdoctoral fellow in my lab, and they together did this work. I am primarily a neuroscientist, and my lab is a neuroscience lab primarily. Some years back, in studying the neural control of flies' locomotion, we got into the biomechanics of locomotion. First, trying to understand the biomechanics of the flies' locomotion, then trying to understand biomechanics of locomotion in general. And our main interest here is to try and develop a simple yet general model that can describe locomotion quantitatively across all gates and speeds. And to this end, what we do right now is try to evaluate simple models against data collected from two very disparate walkers. One is the flies, and the other is a human. And we choose these model systems because they are different in size and leg numbers, but also because they have very different gait transitions, and most importantly, flies turn out to walk at extremely slow speeds, and therefore allows us a large range of speed to sort of test our models against. And the kinds of models we are interested in is simple models like you have heard several times today, like IP and SLIP. And traditionally, IP was supposed to be a good model for walking because it nicely explains the mid-stance maxima in the height of the center of mass. And SLIP was considered a good model for running because it nicely explains why you have a mid-stance minimized speed due to the compression of the spring. But 2 decades earlier, these people wrote a similar paper. 2 of them are sitting here amongst us, and they realized that one big flaw of IP is that it cannot produce the M-shaped GRFs that you see in walking, and that SLIP can produce these M-shaped GRFs. And with that, people realized that SLIP can be a useful model for both walking and running because it can describe kinetics of both walking and running. And since then, we have obviously come a long way, and another seminal study is where people from David Remy's lab show that all common bipedal gait can actually emerge from the D-SLIP model. Now, what we are doing is we are trying to assess not only whether D-SLIP can produce these gaits, but whether they produce these gaits in a way that it can be a quantitative model for animal locomotion. And we started assessing this using Drosophila locomotion or fly locomotion, and we found that SLIP is actually not at all a good model for fly locomotion, and that's the work I presented in last dynamic meeting, and it's published now. And so today what I'm going to talk about is do a similar set of analysis for assessing D-SLIP as a quantitative model for human walking. This is an ongoing work, and what I'm going to present today, most of my talk today will be about asking how good is D-SLIP at capturing the M-shaped sort of walking range of humans. And what are the physics or mechanical principles that determine these limits. And in the second part, short part, we'll fit D-SLIP to models of human walking. So let me get started by saying something that many of you probably already know, which is that which mode D-SLIP works in, the many modes that David Revis's law described, is determined by where the center of mass is in relation to the equilibrium point. And what this means is, so this is just the gauge cycle on the top, and a schematic of that gauge cycle. Here is an expanded view. The solid line there is the natural length of the spring, and then the dotted line is equilibrium length. And with the spring being compressed, this delta equilibrium amount, your spring forces precisely balance out your gravitational force. Now, because the forces at mid-stance is downwards, so therefore, for walking gates, the gravity must win out at mid-stance. Therefore, your delta naught should be lower than delta EQ, and therefore the height of your center of mass must be higher than the equilibrium height. And if you agree with this, then you get the M-shaped GRF right away, because you will have a mid-stance minima in your GRFs, and you will have two maxima at the middle of the double support phase. And then you will go down to zero as you take the foot off. You can play the same game with the center of mass being below the equilibrium point, and now you're going to get a mid-stance maxima in GRF. You can play the same game with sort of multiple oscillations, and using this kind of logic, and with one refinement to take into account the angular speed, you can get this kind of table which describes when you're going to get which gate for all the single oscillation gates. So essentially, which gate you are in will depend on your gamma, which is the spring constant, non-dimensionalized spring constant, and omega, which is your velocity. So what we can do is ask what are the speed limits for each of these gates in the D-slip model, and we do very similar kind of things that others have done, except that we are looking at this parameter space slightly differently. We are varying gamma on the y-axis here and omega on the x-axis, and these colored regions that you see are regions where you're going to get limit cycles with both single stance and double stance phases. And what you can see is that you have in the orange the multi-oscillatory phase, the black schematic is black stuff there. This thing is the GRF, and you have the kinematics underneath it. And I want to make a couple of points here. First, multi-oscillatory gates only occur at low speeds, and they are rarely used by humans. They might be, but as we saw in the talk in the morning from Tom. But much of the human locomotion fits with this M-shaped GRF that's in the middle, which describes much of the human walking range, which is good. That means D-slip might be a good model for human walking. But also notice that you have other gates possible at these speeds, right? If you draw a line like that. And so the question is, why do we prefer the M-shaped GRF? Now, one possible reason is that it's energetically favorable. Now, obviously, D-slip is a conservative model, but if you take the spring energy stored by the spring as energy that's going to be lost during actual human walking, then you get this nice result that the M-shaped GRF is preferred. Because you can see that this lobe here is much lower energy than the other lobe. Alright, so now what I'm going to spend the next few slides is trying to understand how this limits, what results in this limited band of M-shaped GRF. And to this end, what we are going to do is take an analytical approach by simplifying slip further and using equations of motion where the angular motion and the radial motion or the vertical motion are decoupled. And this is shown here. These are the full equations of motion, and we are so this is delta and theta. delta theta, and we are going to decouple it, i.e. remove the theta terms from the delta terms, and then you simply get delta as an motion, or the radial motion as an oscillation about this equilibrium point shown by the dotted line, and about 1 by omega. Now you can, this reduces to the theta motion is obviously determined by a speed that determines how fast you are going forward, and you can define a new coordinate phi that describes the radial motion as an oscillation, and the period of that oscillation is going to be proportional to your spring stiffness. So with that, we can get analytically some sense of when you are going to get a limit cycle by asking by synchronizing these two coordinates at the point where single stance ends and double stance starts. So these star coordinates are those coordinates. And so upshot of that is you get these relationships which describes how theta phi is related to the speed of locomotion. Now, one thing I won't have time to go into, but we can discuss later, is the theta star varies very little with speed because it's just determined by geometry. Whereas phi star will go all the way for n sub here between pi by 2 to 3 pi by 2, which means that your omega naught is, you can calculate omega naught or a lower bound by simply putting a high value of phi star. And this is shown here. You can ignore the other dotted lines, just focus on number 2 here, and you can see that matches really well what we see from Diesel. Now, to take care of the other band here, you also have to consider what happens in the double support phase. And what happens in the double support phase is, or the most important thing, is the velocity redirection that others have described. And the problem with velocity redirection at high speeds is that your double stance phase becomes shorter and shorter, making it harder to do that velocity reduction. And this is shown in more detail here. Your double stance time decreases as you speed up. The change in velocity you require increases because you're moving at a faster rate, and that means you require much greater accelerations. And that means, but your actual acceleration is highly bounded, and therefore from those considerations you get a maximum omega naught that you can achieve. And if you plot this now, this is how it looks, the upper bound from these considerations, and you can see that although it does not match the D-slab perfectly, it is close enough for us to claim that what is important here is that what limits the upper range is the inability to do the velocity redirection at high walking speeds. So now I'm going to switch gear and very quickly tell you about our attempts to fit the data. What we have done is fit a single limit cycle to the entire walking bout, each walking bout at a given speed. And this is one of the results. You can see that D-slip does a very good job at that speed. So that's the one we are seeing. But as you go either lower or higher from that speed, the fits become worse in different ways. And then if you plot these parameters against those points, what you can see is this is at the middle of the range where the fits are the best. And at 2 miles, 2 miles and 3 miles, you're getting to the edge of those distributions. Meaning that the D-slip, bottom line is D-slip works really well, but for very limited range of speeds in very fair. So I conclude by saying that we think that the low limit for the MSIP GRF is good. That is, D-SNP is a good model, and we think that as you go at to lower speeds, you are going to see multiple humps, and that should work out fine. But we need a better model to describe how humans do the change in the redirection of velocity in the double support phase to get a better model of human walking. So that's all I have. Thank you for listening. Go ahead, Andy.
So you were moderately critical of the slip model, but why should the slip model be a good model at all? Like it does some, you could say it's curve fitting or it's fortuitous, but is there a reason to think it's a model that you could work with or predict with, or just to be frank, I don't get it. But so why do you think it's a good model?
As opposed to?
Inverted pendulum model, I think is a good model. The generalized inverted pendulum, I think, is a good model. But the slip model, I don't get, actually.
I think we found slip model attractive. We started with fly, and we started with slip as the base model, and then we could modify it to make it work to the fly data very well. Now, with respect to human walking, I think slip is still a better starting point for the questions we want to ask, which is kinematics and kinetics.
Then inverted pendulum?
Yes, because of the M-shape GRF.
The MC was what?
The M-shape GRF,
The inverted pendulum has that also. It's just a delta function instead of a pump.
I see. All right, yeah, good point. Yeah, I'll think about it. We never really considered inverted pendulum, thanks to people sitting in this room. Our interest in biomechanics sort of postdates the work by Gayar Black hand paper, so we always went it like we never really considered IT. Yeah, fair point. I don't have a good rebuttal other than that. Yeah, go ahead, David.
Can I throw in something from me behind? And I'm just curious how what you see matches my experiences with. So number one, the walking on springy legs is a matter of frequency matching. You do 2 vertical bounces with 1 leg swing. Right? So
Yes.
Running, you have a different match where you have 1 vertical bounce. So that's where the M shape comes from, because
Yes.
there's 2 oscillations. The transition, the upper limit is given if you increase energy, the bounces get higher, because it's an oscillation, also the valley gets lower, and you keep doing that, your leg lifts off and you transition into skipping. Is that one of the limits that you were showing?
Exactly. So I think everything you said is exactly what we observe. That is, the upper limit comes about because your center of mass is moving very close to natural length already, and it turns out that to get that limit, we have to consider both the single stance synchronization of the oscillation as well as the inability to do the velocity redirection in the double stance phase.
But you have an angle of attack, right? So there's no swing dynamics.
Yeah, I think we do have step length. It's probably the same thing. So we fixed for each of these graphs I showed you, or all the graphs that I showed you was for a single step length.
Okay.
And then we do, so I think angle of attack and step length is going to get the same thing. The reason we do it this way is because in the end our goal was to fit human data, and therefore we wanted to fix whatever dynamics we do with the step length of the human. Thanks. Thanks.
Responsible.